Welcome to BKW Physics. I'm Mr. McConley. We're going to talk about resonance today, how it relates to natural frequency. So let me just walk you through some definitions to start out, and then we'll get to some more interesting stuff, which is some demonstration. So when a material is driven at its natural frequency, it results in a large increase in amplitude. Some simple examples of this. If you think of the first one I have labeled here, a swing. If you think of a kid or a person yourself sitting on a swing, and someone else is pushing you, or you're pushing someone on a swing, if the swing goes out a little bit, and then you time it right, and you push again, and you time it right, and you push again, what will happen to the swing? It'll have a large increase in amplitude. That's only if you, like I said, push it right. What do I mean by push it right? You gotta have your timing right. You've got to push it so that it corresponds to the back and forth pendulum motion of the swing. That is being driven at its natural frequency. So let's look at what natural frequency really means. Natural frequency is the frequency at which an object will vibrate when it's struck. You might be able to hear that sound. That right there is its natural frequency. Now, if I were able to push it at that speed, which is really hard because that's a really high frequency, but if I were able to push it at that speed, the thing would have a large increase in amplitude and sound like boom, and it'd get louder and louder. If I could do that, I can't push it. The idea of hitting something also could be called a forced vibration. You're forcing it to vibrate at its natural frequency. So what we want to do now is we're going to walk through a few of these. Some of these I'll just explain in words, and then we'll spin the camera around, we'll do a few demonstrations. Let's jump to the Army brake stride one. So if you're in the military, which none of you are right now, but if you're in the military, when they go marching someplace, they go, 1, 2, 3, 4, you know, and there's a rhythm to it. Everyone's walking with the same rhythm. They like to be organized, they like to be orderly, and they like to do things the same. Great. Why do they always break stride when they go across bridges? That is military, that's what they do. They always break stride. So in other words, and then why?
So they don't shake the bridge at one frequency.
Yeah, because if everyone's walking with the same frequency, you can imagine right foot down, right foot down, right foot down. All of a sudden, you're starting to get this sort of effect. Everyone's stepping down at the same time. This might not be a problem, but it might be a problem depending on the bridge. If you happen to hit the natural frequency of the bridge, because you know bridges move. If you ever stood on a bridge and a truck goes across, the bridge goes whoop, whoop, whoop. You know what I mean? You felt that? Can you relate or no? There's not a lot of bridges here in Bern, but if you go down to Albany, there's longer bridges. When trucks go across, they vibrate. Well, if everyone's walking and they start vibrating the bridge at that natural frequency, it will exaggerate it, increase the amplitude. That bridge will start going whipping up and down. It's bad. The extreme case of this happened in 2001, and I have an article here about it. In Jerusalem, there was a wedding reception. And in this particular culture, they do the dance of the chair where they take is it the groom?
Yeah,
you know about this?
They do the groom and bride. And
okay.
Usually it's the family as well.
And they put them in a chair, and then a bunch of stronger guys lift the chair up with the person sitting in it, and they go, they dance around like this. And everybody is going, what do you see coming here? Well, unfortunately, they picked a wedding hall which had a natural frequency of exactly that dance, which is just dumb bad luck, and it started vibrating. They collapsed. This is a 600-person wedding reception. They collapsed the building and people died. That was in 2001. Horrific, but true. I can't make these things up. That is crazy right there, but that really happened. They vibrated the building apart doing the wedding dance. Okay? Pretty rough. I think for the next ones, let's spin around to the back of the room. Now the first one we're going to do is kind of a classic here, and I'll start. These are two, champagne glass, wine glass, and I'm using some Snapple here because it's kind of sticky stuff. And what I want to happen is I want my fingertip to kind of stick to the glass and then slip, and then stick and slip, and stick and slip. And when that happens, you start forcing vibrations, or in other words, you hit the natural frequency of the glass. Now on this particular glass, all we can see, it's more of a visual thing. Can you see the water shaking in the video? The water is actually vibrating, and from my perspective, I can hear a really low note, like a humming sound. That's vibrating at its natural frequency. This glass, I think, is a little bit more interesting. There it goes, it's coming. Having trouble holding the bass still. It's actually vibrating so much, the sound's not that great, but it's vibrating so much that it's like, I can't even hold the bass, it's like slipping across the table. That whole glass is just shimmering. An extreme example of this would be those opera singers that can hit a note and go, ooh, whatever that note was, it kind of sounded high to me, like, ooh, and they can sing that note, and they can sing it loud enough that they'll get the glass to break. Because the thing will just start vibrating, and they're forcing it to vibrate more, and then it falls apart. Okay, that's a forced vibration. Pretty cool stuff. Resonance. This next one here, go this way. We'll start with just one. This is a tuning fork. It is a 256 hertz note, which is a C note. That's a C. Now that is sending out longitudinal waves. And now I'm going to use another one, which is a tuned one, so I can move this up and down until these two notes are matched. And I had a student a couple years ago tune them so they were at the same note. Now, when I do this, and I send it out for a while, can you hear it? People up close can probably hear it. Let me move it a little closer and make it a little bit louder. It's kind of hard to hear with the fan and the heater unit. Hearing it that time? So, what you're doing here, what are we doing here? I mean, seriously, like, the air is bending the metal? Yes. This is a longitudinal wave. It hits this one. Boom, 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 boom. Now normally, that really wouldn't do much. But this longitudinal wave that's coming from here is exactly at the natural frequency of this one. So when it hits it, it starts vibrating this one at the natural frequency because they're the same. And then this one starts making the noise. Pretty cool, huh? Let's do it one more time. See if I can even move it a little closer. I wish it was louder is my point. Kind of hear it a little bit? Alright. That's the forcing vibrations across two tuning forks. The last thing I want to encourage you before I wrap this up today is go check out the Tacoma Narrows Bridge. Now, you've seen that air can bend metal. Do you believe that something can vibrate a bridge so violently that a steel and concrete bridge will fall down? The answer is, you better check it out. Physics.